up to now, we've only worked with one trait, one set of genes. But now we're starting with two traits. We're going to work with two traits together. So it's called dihybrid crosses, and the text number, page number is 614, I think, 613, 614. So in order to teach you this, I'm just going to go through a problem with you. So there's a problem that Gregor Mendel did. He was using pea plants. He found that the genes for seed color, or he deduced the genes for seed color and seed shape are actually on different chromosomes. And the genetics looks kind of like this. He discovered by working with them individually that yellow is dominant over green and round is dominant over wrinkled. And I am actually doing the same problem on the board here that you find starting on page 613 and on to 614. I'm doing the exact same problem. Gregor Mendel started off by taking a completely homozygous yellow-seeded, round-seeded plant, completely homozygous, and crossing it with a green, wrinkled-seeded plant. The key to dihybrid crosses is to be able to come up with the gametes. And the thing that you notice here is that when you make a gamete from this, you must take one of each set of genes and put it in the gamete. There must be a Y and an R in the gamete so that when the offspring, and notice the only possible gamete for the first parent is big Y, big R, and the only possible one for the second is small y, small r, no matter which combination of Y's and R's you put together. So the only possible offspring you could get from this cross is a dihybrid offspring. That means heterozygous for both traits. That's the only way you could get that. Of course, Gregor Mendel wanted to try. What would happen if you take the F1 and cross them? So what happens if you cross two dihybrids, like two totally heterozygous individuals, heterozygous for seed color and seed shape? And here's the key thing again. Look at what you can get. The gametes must be every possible combination of a Y and an R. So actually, the gametes for this, there's 4 possible gametes for each parent. This is the principle of independent assortment. Independent assortment. When the genes go to the gametes, they assort independently. The Y's, since they're on a different chromosome than the R's, could go either direction, but all gametes will have at least one Y, or will have one Y and one R, and every possible combination of Y's and R's is there. So you'll notice when we make the Punnett square, you put the gametes from each parent on either side of the Punnett square, and you get this monster Punnett square. And you'll notice that the way you fill in the Punnett square is you just take the Y's from the side and the Y's from the top and put them into the square. But again, notice what's been done. The Y's always stay together. The capital always comes before the small letter. This very same chart can be found on page 614, where you actually can even see the phenotypes if you look at them. All the ones that are yellow round and all the ones that are green round and yellow wrinkled and green wrinkled. On this chart, I made a check mark for each one that was yellow round. And out of the 16 boxes, there were 9 yellow rounds. And I put an asterisk beside each one that was yellow wrinkled. So there were 3 of those, yellow wrinkled. I put a little circle beside each one that was green and round, and there were 3 of those. And of the 16, there was only one, very in the bottom right-hand corner, that was green and wrinkled. So this 9 to 3 to 3 to 1 is a classic dihybrid cross ratio, 9 to 3 to 3 to 1, just like the 3 to 1 ratio is classic for the monohybrid cross. This is classic for the dihybrid cross. Here might be a way to get at the same concept and understand whether you know how to do gametes by just saying, what if you crossed a homozygous yellow wrinkled seeded plant with a heterozygous yellow homozygous round seeded plant, and those were the parents, then those would be the only possible gametes from the parent on the left and the parent on the right. Those are the gametes. Put those on a Punnett square, and look how small the Punnett square is. All of the offspring from that cross will be yellow and round. But half of them will be doubly heterozygous, and the other half will have 2 big Y's and a big R and a little r. So I would be testing the same concept by giving you a question like this than the previous page where we had to make a Punnett square of 16 large. So you need to know 2 rules of probability. First of all, chance has no memory. So if a family has 3 boys and they say, well, what are the chances we're going to get another boy? You would say what? 50-50. Right. 1/2. Because chance has no memory, doesn't remember that you've already got 3 boys. However, if you said at the beginning, before they had any kids, what are the chances they're going to have 4 boys, then you have to use the product rule. The product rule says the chances of the individual events must be multiplied. So if you had said, what are the chances a family will have 4 boys, then you'd have to say something like this. Well, the chance of the first boy is 1 out of 2, and the chance of the second boy is 1 out of 2, and so on. So a chance of having 4 boys would be 1 out of 16. Or, since fractions might not be your strong point, you might say instead 0.5 times 0.5 times 0.5 times 0.5, or 0.0625 is the probability, fairly low probability of having 4 boys. One reason to teach this right now is that if we took that same big yellow round situation, doubly heterozygous, and did it on 2 separate little Punnett squares, did the yellow heterozygous and the round heterozygous on each separate square, this is very quick to fill out. We know this classic 3 to 1 ratio. But then if I asked you, what fraction of these are expected to be yellow round, you would use the product rule and you'd say, well, what's the chance of being yellow? 3 out of 4. What's the chance of being round? 3 out of 4. What's the chance of being yellow round? 3 out of 4 times 3 out of 4, or 9 out of 16. And you can do that in decimals as well. You can go 0.75 times 0.75. So what percentage of the offspring, or what fraction of the offspring? So you could actually calculate every single one of these just using these 2 separate little squares. So some people use this method to try to analyze 2 sets of genes and work them out separately, and then put them together to whatever the question is asking. The questions that go along with this lesson, the best ones are page 619, 1 and 2, and on the problems worksheet, 9 through 16. Although number 11 is a little bit challenging, so if you're doing it, you can kind of skip 11 if you're struggling. We'll talk about it in class.